This video is on vapor pressure of solutions. So a non-volatile solute lowers the vapor pressure of a solvent because the solute particles get in the way of the solvent particles. If I have a pure solvent here versus a solution, if my pure solvent would like to go from the liquid phase to the vapor phase, it simply just needs to muster up enough energy and jump out of the liquid phase to become into the vapor phase. However, if there is a solute dissolved into the solvent, those solute particles are going to prohibit the solvent particles from getting out into the vapor phase. Therefore, the solvent particles will have to gain more energy before they can get around the solute particles to jump out to be a vapor. Solutions have physical properties that are different from those of the pure solvent. This is because of our solute particles getting in the way of our solvent particles. So examples of this are antifreeze or putting salt on icy roads. The salt gets in between the water molecules on the icy roads. So if this is my water and this is the salt, my salt gets in between the water molecules, and then my water molecules really have to lose a lot of energy to get down into the configuration they want to get into to freeze, because my solute particles are in the way, so I have to force them out to get to freeze. Whereas if they weren't there, it'd be easier for this solvent, my water, to come together and freeze. And then antifreeze works similarly, where we don't want it to boil and we don't want it to freeze in our engines, otherwise that would be bad for our engines. So antifreeze is a mix of water and propylene glycol, I believe, and that could be wrong. But it's a mix of two different liquid solutions, or two different liquid solvent and solute, and same idea here as here, the solute particles get in between the solvent particles, and it prevents it from both boiling at low temperatures and freezing at higher temperatures. So it's going to lower the boiling, or lower the freezing point and increase the boiling point. So if I were to have a solution, and my solution is next to an open container of pure solvent, in this case water, my water is going to jump into the vapor phase and start heading towards my solution to start diluting the solute in the solution. So this is going to happen, and it's going to continue to happen until my water container, my pure solvent container, is empty and all of my pure solvent has vaporized, it's vapor phase, and gone into my solution. So after a period of time, all the water is transferred to the solution, and this has to do with the vapor pressure difference between a pure solvent and a solution. So this leads us into Raoult's law, and Raoult's law says that the solvation of the process of them becoming a solution of an ionic compounds lowers vapor more than is expected from Raoult's law. And vapor pressure lowering depends on the number of solute particles and ionic compounds dissociate into those particles. So here I can see that the pressure of the solution is proportional to my mole fraction of the solvent and the pressure of that solvent. So over here I would have no solvent, and here I would have all solvent. Okay? And along this line would be the vapor pressure of our solution. Our mathematical formula for Raoult's law says that the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of that pure solvent. Knowing this, I can go through an example. If the vapor pressure of water is 23.76 torr at 25 degrees Celsius, calculate the vapor pressure of 20 grams of sodium chloride dissolved into 120 grams of water at 25 degrees Celsius. Well, here what's given to us is the vapor pressure of our pure solvent, which is our 23.76 torr. We are told the mass of our solute, the mass of our solvent, and it's all at the same temperature, which is what we need to happen. So if we're trying to find the pressure of our solution, I need to know the mole fraction of my solvent and the pressure of my pure solvent. I know the pressure of my pure solvent, that's this. So this is my P0 of my solvent. And I need to calculate my mole fraction. So to do that, I need to take the moles of my solvent divided by my total moles. So I need to calculate my moles of sodium chloride, and I need to break that down into particles. And so I know that I can get to moles here, but then for every 1 mole of sodium chloride, I have 2 particles. So this is my moles of solute particles, okay, because they break apart, they dissociate into their 2 ions. So that matters for us. And then for my water, I need to take my mass of water and convert mass to moles. And water doesn't break apart into ions, it just breaks into its individual molecules. And so I just have 6.67 moles of water molecules. So to figure out my mole fraction, I take my moles of water molecules divided by my total moles in my solution, and I get a mole fraction of 0.907. So I have my parts. I know my pressure of my solution is equal to my mole fraction of my solvent times the pure vapor pressure of my solvent. So I multiply those together and I get the pressure of a solution to be 21.6 torr. So what about liquid-liquid solutions where both the liquids are volatile? So that's thinking back to our antifreeze problem. Well, here I can plot both sets of information. I have my mole fraction along the x-axis, just as before. I have the vapor pressure of my one solution, and then one solvent, and the vapor pressure of my other solvent. So at the beginning over here, this is where I have 0 of my A solute or solvent, but I have 100% of my B solvent. So I am 100% solvent B, where here on this side, here I'm 100% solvent A, it's the top of A, and I'm 0% solvent B. Okay, so we can kind of do those up. So of a solution, after I plot these, I connect where my 100% of B to my 100% of A. I connect that, and this line is the vapor pressure of my solution. Okay, so that has to do with the mole fraction. And I figure out my mole fraction, and along that line of my mole fraction, let's say I'm 50-50, my vapor pressure would be here. If I'm 75% or 70.75 of A and 0.25 of B, well, that would be most, 0.75 of A, so that's over here, 0.25 of B, so that'd be like here. Okay, so that's along this line. This is a diagram of an ideal solution, so one that obeys Raoult's law. So that means that the total pressure is equal to the sum of my partial pressures of my pure solvent A plus my pure solvent B, which we know has to do with the mole fractions. And so it really is the mole fraction of my pure A plus the mole fraction of my pure B. So this is when we have 2 liquids together. Okay. Now, as always, we have exceptions. So we have 2 different deviations from Raoult's law. We can have a positive deviation from Raoult's law, where I have a polar mixed with a non-polar solutes and solvents. So we can see our dashed lines are the way it was before, so just like this with the straight lines. But a positive deviation means it's going to be higher than we expect, and all these lines are going to have this positive bump here. Okay. I can have a negative deviation, and a negative deviation where I have a dip in my partial pressures, or my pressures of each. So it dips down. So I'm finding out it's lower than I expected. Where we have no deviation is when we have a nonpolar mixed with a nonpolar solvents. So to look at an example with this, I have a solution prepared by mixing 5.8 grams of acetone, which is CH3, COCH3, with 11.95 grams of chloroform, which is HCCl3. At 35 degrees Celsius, the solution has a total vapor pressure of 260 torr. If the vapor pressure of pure acetone and pure chloroform at 35 degrees Celsius are 345 torr and 293 torr respectively, is this an ideal solution? So I need to figure out where is my vapor pressure when I have 345 torr and 293 torr respectively of these pure solvents. So that means that this point here for, let's say A is my acetone. This is going to be, try to get both on here for you. So acetone is 345 torr, so this is 345. Ooh, we should make acetone this guy because it's higher. So this is acetone, and this is 345 torr, for our example. And then this one is our chloroform, which is 293 torr. And so we're going to find out if 260 torr is above, on, or below our line. If it's above, we'll have a positive deviation. If it's on, we'll have no deviation. And if it's below, we'll have a negative deviation. So we're going to see what it is. So I know that my total pressure is equal to the sum of my mole fraction of A times my pressure of my pure solvent A plus my mole fraction of B times my pressure of my pure solution or my pure solvent B. To do that, I need to figure out their mole fractions. I know my starting masses of acetone and chloroform, both of which are covalent compounds, so they're not going to break apart into ions like they would an ionic compound, so I just need to go to moles, not particles, because they're already in their smallest particle, which is their molecule. So I convert my 5.8 grams of acetone to moles, I get 0.1. I take my 11.95 grams of chloroform to moles, and I get 0.1. So since each occupy the same number of moles, that means their mole fraction is each 0.5, or a half. So then I calculate my total pressure using my formula, my pressure of my acetone times my mole fraction plus the pressure of my chloroform times my mole fraction gives me 319 torr. So on this line here that we're looking at, on this line here, this X here is 319 torr, is here. What I have observed is 260 torr. So what I've observed is here of 260 torr. So because what I've observed is lower than an ideal solution, that means that my solution here has a negative deviation. This also makes sense because we learned that when I mix two polar mixtures together, it'll have a negative deviation, and both acetone and our chloroform are polar. So, is this an ideal solution? No, because 319 is higher than the actual vapor pressure of the solution of 260 torr. So the solution must have a negative deviation from Raoult's law. So 319 torr would be its ideal pressure, but our actual pressure of 260 torr is lower. Since the actual pressure is lower than the ideal pressure, we have a negative deviation from Raoult's law. This makes sense because we have hydrogen bonding between our substances. So between our acetone here and our chloroform here, between this partial positive hydrogen on our chloroform and our partial negative oxygen on our acetone, we have this hydrogen bonding interaction. Remember that it's not an actual bond. These are intermolecular forces, so it's an interaction between my molecule of chloroform and my molecule of acetone. They're attracted to each other.